That's what we imposed. What else? We also assume that this is true. We haven't used this assumption actually, but this says that there is a chance that the family size is bigger than 1, right? If A0 plus A1 is already 1, that means you cannot have more than 1 offspring. But because there are still some chance, you can have A2, right? Or A3. We will use that assumption today, but yesterday we haven't used this assumption. And lemma 1, we proved that in a branching process, Z, right? Zn. All non-zero states are transient. We haven't said anything about state 0. It can be transient or recurrent, right? What else? And then, yes. Given the mean of the offspring, mu and sigma square, for the x, right? For the offspring size. We will be able to find the mean of the generation size by calculating mu to the n. For the variance, and then we use that. We use this formula to classify the long-term distribution, the long-term mean, right? By using calculus. If mu is less than 1, then you pull it out. If mu is less than 1, then taking the limit will be 0, right? That means in long run, the average or the mean of the generation size will be 0. If mu is 1, then it's stable, always 1. If mu is bigger than 1, then it will explode. For the variance, where is it? Yeah. Oh, before we look at the variance, we look at this first. I exclude one special case, which is subcritical case when mu is less than 1, right? When mu is less than 1, we prove that. What did we prove? Page 5. Oh yeah, we prove that PE is 1. What is PE? What is E? E is the event that the population is ultimately extinct. It's always extinct if mu is less than 1. Okay, this lemma says that. We cannot follow this proof. We cannot follow this proof to get a conclusion for PE when mu is bigger than or equal to 1. We have no conclusion using this. Okay? But today we will look at that using PGF. And then we look at the variance. We derive this already. Given that sigma squared is the variance of the offspring, the size of the offspring, then we can derive variance of Zn. This is easy, it's just n sigma squared if mu is 1. If mu is not 1, then we have a more complicated result here. But using that, we can also conclude this, right? When mu is less than 1, both mean and variance will tend to 0 when n goes to infinity. When mu is 1, the variance is still, when mu is 1 is this, right? You can see that if mu is 1, what happened? When you take the limit of this, it grows linearly, right? Isn't it? Take the limit of this. You're going to get sigma squared, 2 sigma squared, 3 sigma squares, and so on, right? So it grows. When mu is bigger than 1, here, also grow. So for this case, both variance and mean grows. And after that, we learn PGF. What is PGF again? Generating function. By definition, we just find expectation of s to the x, right? X can be any random variable. And yesterday we see some properties of this. The first thing is that if I plug in s equal 1, so for any generating function, if I tell you that g is a generating function of a random number x, then g1 is always 1, right? This is because we plug in 1 here, you're going to get back the sum of the PMF. That's why it's always 1. Is a power series where the coefficient is just this PMF. Right? What else? If you know that 2 variables have the same PGF, then they have the same distribution as well. That's property 4. And example 1 shows us how to find a PGF of this uniform random variable. We will not look at that. And then for geometric distribution, this is the PGF, right? So basically, just find expectation of s to the x. Page 8. It's a converse. So if you know the PGF, if I give you PGF G, then you can find PMF of x by calculating this. If you want to know whether x is J, what do? Differentiate J times, plug in 0 divided by J factorial. So we would not look at that. And then this example, you know that this is a PGF for one random variable, for a random variable x. Find x. So we just use fact 1 and then we derive that. In fact, PMF is binomial. Okay? I think we finished, we stopped there yesterday so far.